I would like to welcome everyone in this second session of the user forum, which is organized by the Aspect project, developing a new generation of seamless climate predictions to serve climate adaptation. Myself, I'm Panos Athanasiadis, and I work as a senior scientist in the Euro-Mediterranean Center on Climate Change, in brief CMCC, which is one of the key partners in the Aspect project, providing climate predictions seamlessly in all forecast horizons. The scope of today's session is to learn about the progress made in the Aspect project. I should mention that for those who couldn't attend yesterday's session, that the session was recorded and the keynotes, the talks will be made available on the project website. I would like at this point to ask everyone who is not presenting to keep their microphones muted, and while raise hands for questions and alternatively put them in the chat or best in the questions and answer tool. We should mention, of course, that this session is also recorded. The purpose of this recording is to disseminate the keynote talks, while the discussions are recorded only for internal purposes and will not be disseminated. At this point, I would like to welcome our two first speakers. So Dr. Freya Gary is a senior scientist at the Met Office working to improve the inclusion of state-of-the-art climate science into useful and usable climate service prototypes. And Dr. Bina Balan Sarojini, who is a climate researcher at the University of Oxford, Atmospheric, Oceanic and Planetary Physics Department. Bina is an expert in climate predictions and coupled model evaluation. At this point, I will pass the floor to them.
Thank you, Panos. Hopefully you can see the screen now.
Yes, that's right.
Perfect. So, hello. As Panos has said, my name's Freya, and together with my colleague Bina, we're going to share with you an accessible overview of what our scientists in Aspect have been doing during 2023 and where we're going for the rest of the project. We won't be getting into too many of the technical details of the science here. We're hoping this will be accessible talk to people from many different organisations that use climate information or are interested in using climate information to understand present and future climate risk. We hope this presentation will show the breadth of science going on across the Aspect project. Broadly, the areas of aspects that we are going to cover in this talk include the new model experiments that are being created and what our expert scientists in seasonal to decadal predictions are learning from these latest model experiments. Then we'll talk about how we're drawing that learning through into creating new climate information and products that we can then use to help develop tailored climate services that are both useful and usable for your decision making across multiple sectors of society. This diagram shows the range of timescales that as humans we mostly think about, from weather through to climates for the next 100 or so years. And it highlights the range from greater than a few months to 20 to 30 years in the future that is the real focus of the Aspect project. We want to help you get the right information to help you with the decisions you need to make on these relatively near term timescales to help you with your adaptation to climate change. We often talk about weather forecasts and climate predictions. So, in looking across the timescales in between, from seasonal to decadal timescales, we often hear both of those words, forecast and prediction, being used. Here, we've decided to try and use the word prediction for our seasonal to decadal climate information. But if you see or hear mention of aspect forecasts, we mean the same thing. This plot shows different scenarios for future climate change, which represent different possible futures that humanity could follow depending on how fast societies transition away from using fossil fuels like oil, coal, and gas and towards net zero. When we zoom in just to looking at the next 20 to 30 years, we can see that in all of these scenarios, we still expect to see a rise in global warming over the next few years, with some places warming faster than others. We're already experiencing climate impacts around the world, often impacting vulnerable people the most. So there is a real need to adapt to climate change and the increase in extreme weather we will continue to see. In aspect, we can improve on these long term scenarios by using more information about the natural variations that happen to the climate and what our climate looks like now. For example, is it warmer or cooler than usual at the moment? This extra information about what's happening now is part of the seasonal to decadal predictions that we make. And when we look at these predictions then in your area, we can use this seasonal to decadal climate information to give you a better idea of the near future and the risk that you're likely to face from climate change. This improved information can help users make better decisions. Before the Aspect project started, there were already different seasonal to decadal experiments being produced by many of the expert scientist groups involved within the Aspect project. For example, seasonal experiments typically give predictions up to about 6 or 7 months ahead, with decadal predictions going up to 10 years. As we've just mentioned, the climate predictions give better near term information compared to climate projections. Climate projections are really still very helpful for understanding that long term climate change, but the setup of these experiments has always been slightly different. There are these lots of different natural climate variations, which Bina's going to talk a little bit more about later, which last between years or decades, and they happen on top of the ongoing warming trends. They don't tend to happen exactly at the same time in climate projections in the real world, but our seasonal to decadal predictions try to bring these variations in sync. And this helps us provide more useful information for this near term decision making, where understanding those natural variations is really important. An example of a climate prediction on annual average temperature is shown here. So, this prediction was made by the Met Office for 2024 relatively recently. The model experiment suggests that 2024 is going to be warmer than any year before 2023, with the range of global average temperatures predicted for 2024 shown by that vertical green line. So, this suggests that we expect the 2024 global average temperature to be nearly 1.5 degrees Celsius higher than before humans started burning large quantities of fossil fuels in what we call the pre industrial period. When we think about decisions that might be made from this information, for example, a hot summer could be associated with poor crop yields in Europe, as hot summers often tend to be quite dry. And so, if we know that we might have a hot, dry summer coming up, then extra irrigation may be required for farmers to help keep crops healthy. And this would be something that water sector planners would need to anticipate. Another example over the next few years is that the Met Office, together with the World Meteorological Association, have predicted there's a 50-50 chance that we'll get at least one of the next 5 years being over 1.5 degrees warmer than the pre industrial. These are example headline predictions, but these same experiments can be used to make predictions in more local areas as well. The first part of the Aspect project is to make some new experiments to improve predictions over the coming years. And this slide outlines some of these improvements. An important way of being able to tell how good future predictions are is to use the same experimental setup in the past, where we know how the climate behaved. As science moves forward, we're also improving our climate modelling. So, new, improved versions of models are being used in Aspect compared to previous experiments. For example, models are made up of lots of boxes representing areas of the land, ocean, or atmosphere, and these all talk to each other. By making these boxes a little bit smaller, we improve how well we can represent some of the processes in the model. Finally, it's really important that we repeat each model experiment many times to create an ensemble. And on the next slide, I'm going to explain a bit more about why this helps us make better predictions. The reason ensembles are so important is because it's very unlikely that one simulation of the future climate will give a very accurate prediction because of these lots of different natural variations in how the climate behaves. So, one prediction, if we make and follow the red line, will end up in one place. So, it gives an answer that looks really precise. However, we know that if we run the model many times, we get various different possible outcomes. This actually gives us a more accurate answer. By averaging the model simulations together from the ensemble, we get a better prediction than we can from one simulation. It's even better if we can make ensembles of different models from different groups of scientists, which is one of the things we can do within Aspect. Because these ensembles actually need to be quite large, and that requires a lot of computer power as well. We're also creating some new experiments that are longer than the normal seasonal experiments. So instead of predicting the next 6 months, we'll have experiments to help us predict the next 2 or 3 years. And for the decadal experiments, we're creating more longer, so 20-year experiments, as well as these typical 10-year experiments. This will enable scientists to try and make better predictions further into the future. Some of the scientists in the project will also perform even longer experiments as well that will help us understand how the climate of the next 30 years is likely to be different from the climate of the last 30 years. This is actually one of the first ways that we are talking about seamless in the Aspect project, because by filling in these gaps in this timescale, we are creating these seamless model experiments. Here, this slide shows which of our Aspect partners are producing these new experiments, with each centre using different models. A lot of supercomputer power goes into the creation of all these experiments. In fact, we have estimated that the Aspect project will produce up to 2 petabytes of data from these model experiments, which is around 2 million film downloads. I'm now going to pass over to Bina to continue the presentation.
Thank you, Freya. Hello, everyone. My name is Bina. I'm going to continue giving you an overview of the next two exciting areas of Aspect. Firstly, the new learning in Aspect, what our expert scientists in seasonal to decadal prediction are beginning to understand from the latest Aspect model experiments that Freya has just explained to you. Secondly, how we are converting that learning into creating new climate information and products to help co-develop tailored climate services that are both useful and usable for your decision making. Before talking about the new learning and aspect, to those of you who are new to the prediction world, I would like to introduce two common terminologies used in prediction. What are predictability and skill? Then I will share some expert knowledge on our current understanding of where predictability and skill are coming from and how good our estimation of extreme weather events is. So what do we mean by predictability and skill? Predictability is the ability or extent to which future climate may be predicted based on the knowledge of the current and past climate. It tells us how well and in advance we can predict the climate over a given region. Prediction or focus skill is any statistical measure of the accuracy or quality of the future climate information or the degree of association of prediction to the observations. It is based on how well the previous climate could have been predicted. In scientific language, or forecaster's term, the prediction of previous climate is called hindcast or reforecast. Next slide, please. Frey has earlier mentioned the relevance of climate wiggles or variations in predicting future climate. Scientists call it climate variability. These are nothing but natural climate variations that happen to the Earth's climate even before humans have started burning fossil fuels. Some of you may have heard of such natural climate variability, such as El Nino Southern Oscillation or ENSO, North Atlantic Oscillation or NAO. The most important or globally relevant climate variation for global and regional climate prediction is ENSO. I will shortly explain what that is. ENSO includes El Nino and La Nina events, which happen every few years. El Nino happens when tropical Eastern Pacific Ocean is warmer than usual, and El Nino lasts for about 9 to 12 months. Or sometimes the situation can go to neutral or even cooler than usual conditions. And this is called cooler than usual condition. It's called La Nina. So this is represented in the bottom figure. The El Nino situations or events are represented as blue shading, the red shading, and La Nina is represented as blue shade. I will get back to that. Before that, the message of this plot is to explain how the climate natural variations like ENSO is going to impact the prediction over different parts of the world. So let's have a look at the top plot, which shows the rise in globally average surface temperature, which is shown as red wiggles, and the global warming can be seen as the black upward trending line here. Now, what is the takeaway message from this plot is that Frey explained that 2023 was one of the hottest years in record, and we also know that 2023 was an El Nino year. So if we look at the red shadings in both the plots, they show years when El Nino was happening. So the longest, the highest value, positive value in both the plots indicated by the red shading here is the 1997-98 year, which witnessed the strongest, one of the strongest El Nino events. So the point we want to make here is that because of years when El Nino is stronger, we get a window of opportunity, or it gives us enough opportunity to predict the climate, especially over different parts of the world, which is impacted by ENSO. So the representation of climate variability, such as ENSO and the North Atlantic Oscillation, NAO, they are very important for predicting the climate over Europe. And this is one of the key elements in aspect predictions. So what do the models tell us? In fact, we learned about predictability, prediction skill, and climate variability as a source of regional and global climate prediction. So the next knowledge I want to share is that we can make better predictions of temperature than rainfall. This is because rainfall prediction is far more complex than temperature, as temperature is affected both by, for example, a local warmer ocean nearby and remote variations such as ENSO happening in the tropical Pacific. The plot shows the European Center's contribution to Copernicus Climate Change Service seasonal forecast for the last summer. It shows the sea surface temperature forecast produced in March. Warmer areas of the ocean are shown in orange to red colors. The 2023 El Nino, fully developed in summer, is evident in the seasonal forecast produced 3 months in advance. We can also see the warmer tropical Eastern Pacific. Recall that 2023 was one of the hottest years in record. We can see how widespread the warming is around the global oceans. What is happening in the tropical oceans influences what is happening in the world in the coming season, especially in regions impacted by the ENSO cycle. Seasonal prediction skill tends to be better in the tropics than further south or north, such as Europe. Aspect scientists are exploring whether ENSO can be tracked up to 1 to 2 years in advance using novel aspect multi-annual experiments. The takeaway message here is that although El Nino is a locally occurring Pacific Ocean event, as Freya told us, both ocean and atmosphere communicate to each other, and the information gets carried long distance through the atmosphere, making the predictions elsewhere in the globe better. Next slide, please. On timescales longer than seasonal, say for the decadal to multi-decadal prediction, which is also one of the key areas of aspect, the predictability primarily arises from the current observed ocean climate. Predictability also comes from the global warming trend, because we are trying to predict the world which is already witnessing the global warming. So I would like to tell you a little more about how the ocean influences locally. For example, predictability primarily arises from the current observed ocean climate. Knowing what the North Atlantic Ocean does helps scientists to predict European weather and climate in both winter and summer. The plot here shows observed warmer sea surface temperature over the northeast Atlantic coast in last year, June. We can see that up to 3 degrees Celsius warmer than last 3 decades the ocean temperatures are. This helps us predict what European climate is likely to be. This is an upcoming research area and aspect that needs to be studied using prediction models from many European prediction centers. Windows of opportunity for seasonal prediction. So these are 2 examples where aspect scientists find that predictions started when an El Nino or La Nina is happening have higher prediction skill in air temperature and rainfall multiple years ahead compared to predictions started with neutral ENSO conditions. The plots show that rainfall changes for an extreme event during summer 2022, predicted by the UK Metaphysics decadal prediction model, is comparable to rainfall observations. Recall that the Freya mentioned that forecasters need to make many number of model experiments to find an average we called ensemble mean, which inherently reduces the chances of us witnessing or predisposing extreme events. So the new study from the UK Metaphysics suggests that even with an El Nino, even with a La Nina happening few years in advance, one could have predicted the unprecedented Pakistan rainfall well. And this is something aspect scientists are working on using different prediction models. Next slide, please. So this is another example from aspect research. We know from earlier research undertaken by aspect scientists that for the European winter climate, the prediction skill in decadal timescales of rainfall is linked to decadal variations in the North Atlantic Ocean temperatures and the North Atlantic Oscillation, which is another natural climate variation happening in the North Atlantic region. Compared to winter, European summer climate has relatively low prediction skill. So the plot here is another example where aspect scientists have explored potential mechanisms that give rise to prediction skill up to 2 to 3 years ahead for extremely warm European summer. The schematic shows how heat gets built up in the subtropical North Atlantic Ocean, indicated by the pink plus signs, over the 3 years, how it influences the atmosphere above and hence the European summer weather. Extending the skill. User needs are wide-ranging. Depending on the time and spatial scale the information is needed for. For example, a particular user may need climate risk information, whether rainfall will exceed over a threshold, a user-driven threshold in the coming season or decade. So this is information required over a very small location of a single asset, like over a village or a farm or over a river catchment. Sometimes the decadal prediction skill alone is not high enough to provide such localized rainfall prediction. This is an example where new hybrid methodology was provided to combine information from decadal prediction models with that from statistical model based on observations. And it provided climate services to hydroelectric energy sector over 3 Mediterranean river basins. Next slide, please. The most catastrophic manifestation of climate change is the increase in frequency, intensity, and duration of extreme weather events, especially hot, dry, and wet extremes, which we know will happen more often in a warming world, threatening lives and livelihoods of millions of people every year. Scale of extreme weather events in the seasonal to decadal timescales are rarely studied in the past. On this diagram, we show the increase in frequency of different types of extreme events causing damage to society over the past 40 years. This is an area in which aspect will focus on, and aspect scientists have already been involved in a recent study which shows encouraging results on decadal prediction skill of temperature extremes. This is a recent study by aspect scientists which estimates that Europe is likely to experience end-of-century like extreme heat and drought events repeatedly, with events typical to the end of the century likely to be experienced within the next decade. Warm decades over Europe are twice as likely depending on a warmer North Atlantic Ocean. With that, we hope you have got an overview of how aspects, new experiments, new learning, understanding, and new focus projects are beginning to evolve. Thank you very much. I now pass on. Sorry. So I now go on to explain the next exciting area of aspect, which is to create new climate information to co-produce tailored climate services for user needs ranging from different spatial and temporal scales. One of the techniques in creating new climate information in high spatial resolution is downscaling, which is an active area in aspect. Aspect scientists use advanced statistical and machine learning methods to convert coarse resolution information from climate models, for example, from a 60-kilometer scale grid box, to provide useful information about hazard likelihood at the location of a specific asset, like a vineyard or 4-kilometer square area. Next slide, please. The next novel methodology to create new climate info is called temporal merging. This is to provide seamless climate information across different time ranges. For example, Freya explained that there are seasonal prediction models providing climate information in the seasonal range and decadal range. And there are climate projections providing climate info in the time range greater than 10 years. In climate projections, natural climate variations are not represented realistically. As a result, although the long-term changes are predicted, short-term wiggles, the natural variations, may not be in the right phase, and it results in erroneous predictions in the short time scales, which is the time scale often a user needs for actionable information for adaptation decisions. A key innovation and aspect is to provide climate prediction info along timescales where there is a current gap in the forecast horizon, that is, from 1 to 3 years and 10 to 30-year timescales. In the temporal merging technique, we try to provide the existing climate info seamless along the timescales. This means you will get to see the seasonal and decadal timescale information together in a single time series. It is a complicated task, and aspect scientists are developing new methodologies to co-produce adaptation-oriented seamless predictions of European climate together with the requirements of the key users of aspect. Another role for aspect is to promote the availability and accessibility of the existing seasonal to decadal information you can use in the development of climate services. I would like to share with you some information regarding where to look for existing information, as there are many sources of useful online resources on seasonal to decadal predictions from many European organizations. For example, German weather services, the Deutsche Wetterdienst, hosts a webpage with monthly, seasonal, and decadal prediction info tailored separately for basic, intermediate, and expert user levels. I would also like to point out the Shiny apps available on the Barcelona Supercomputing Center webpage for interested users to compute and visualize prediction info, including that of extremes in both seasonal and decadal ranges. The third point to highlight is that the seasonal forecast skill visualization is also available alongside the graphical forecast products link on the Copernicus Climate Change Services seasonal forecast webpage. Finally, new experiments and climate information produced in Aspect will be hosted by the European Centre for Median Range Weather Forecast data servers. I will now pass back to Freya to talk more about how the user-relevant climate services are being co-produced in Aspect. Thank you very much.
Thanks, Bina. So we know that in reality, any organization is making decisions about the next quarter, the next year, or when considering climate change, maybe 5, 10, or 50 years into the future. And that's true across a range of sectors, from agriculture to humanitarian or the health sector. When decision making in the near future over the next year or two doesn't account for these long-term impacts from climate change, there's a risk people may make decisions now that may make things more difficult for them in the future. They may adapt in a way that actually leaves them more vulnerable in future rather than more resilient. For this reason, it's important that decision making is consistent across different lengths of time into the future. So we've talked about seamless model experiments and seamless data, but also in our climate services, we're going to be trying to help support seamless decision making around climate adaptation. We're working closely in Aspect with 5 organisations from different sectors. So in the Aspect project, we're calling them super users, although we're obviously continuing to engage with a much broader range of users through these user forum events and other activities. So the first super user is from the agricultural sector, Cordonu, and they're interested in understanding how climate variability and change is impacting on spring frosts and water availability. Aspect will help support their decision making to promote better crop growth. The second super user is actually a bit broader than just one organisation. It's the pensions sector. And we're engaging with several organisations to help develop this case study, including pensions expert Professor Ian Clatcher, a company called Clearglass, and the pensions regulator in the UK. The pensions sector are concerned about climate risk, but largely do not currently use climate information in their decision making in a meaningful way. By creating examples of how climate risk can impact pension portfolios, Aspect will demonstrate how climate services can usefully help decision making in the financial sector. In addition, improving tailored education around climate risk to the pension sector will help support investors to be able to make decisions which lower their exposure to climate risk. The third super user is the governance sector. Aspects working with the EU mission for adaptation, which is helping to support regions to understand their climate risk, aiding strategic adaptation, climate service utilisation, and early warning systems improvements. The case studies focusing initially on the Emilia-Romagna region of Italy. It's one of the most hazard-prone areas of Italy, through engagement with their regional agency for the environment. So you can see here in this overview diagram how some of the decisions being made by these different users from different sectors span the different seasonal and decadal prediction timescales that are the focus of Aspect, and gives a little bit of more insight into the types of decisions being made in these sectors. There's, of course, many other decisions where these climate predictions and projections will help too, but these 5 studies are the main case studies we'll be working on an Aspect. We've recently introduced 2 new super users to the project from the disaster response and the humanitarian sectors, and you're going to hear more about these case studies in the next part of the session. And of course, we are looking beyond these 5 super user case studies to other users in many different sectors, because we know many other organizations and sectors will find seasonal to decadal climate information really useful in their decision making. So we want to provide examples of new prototype climate services that we develop in Aspect that can also be used by other organizations and sectors, and that can be adapted for the different needs and decision making contexts that different organizations have. So this scaling of climate services, as we call it, will help us to deliver more impact from the project overall. So it's really important for users attending today that you're a really important part of the project. And please do keep engaging with our user forums and the discussions that we hold, as well as other activities that you'll hear about through our website newsletter and social media. As users of climate information, you're a really important part of the project, and we really appreciate your input. Thanks very much for listening to this overview of our Aspect progress. And now I'll hand back to Panos to chair the questions. We will continue with a bigger focus on these new super users and sectors, which I very briefly mentioned in the last talk. The new sectors that we're focusing on, as you'll have seen in the summary diagram, are the humanitarian and disaster response sectors. So, Save the Children International will be working with the Barcelona Supercomputing Centre for one of the case studies, and British Red Cross are going to be working with the Met Office on the second case study. And we'll talk a little bit more about might be involved in these case studies, although this super users were selected from a competition only just before the break for the Christmas and New Year holidays. So we are in a very early stages with conversations with these super users, but this is to give you a little bit of a flavour of what we're thinking of the direction for the Aspect project. So Save the Children International are really interested in how climate services can be developed to help them provide adequate water and nutrition and sanitation and hygiene and understand these issues. Save the Children International do a lot of work helping to protect maternal and child health around the world. And so understanding these issues is really important for them. These are really health issues. So this is also almost a health sector type project, and it's a very topical area of climate and health. So at COP 28, which was actually not this month, last month, 128 countries endorsed a new climate and health declaration, which acknowledged the growing health impacts of climate change on communities worldwide. So with this case study, we help support the focus on this issue. So we are actually going to focus with the Save the Children International initially on the European neighbours of Africa and the Middle East. These learnings from these regions will have very high relevance to parts of Europe as the climate continues to change and extreme hot temperatures become more common. The climate services co-produced with Save the Children International will cover the seasonal to multi-annual timescale. And these predictions being produced by Aspect will help Save the Children look at these issues, but also how they might affect the movements of populations on longer timescales. So we all know that migration is a very topical issue affecting Europe. So it may be that the climate services developed by Aspect will also help support adaptation, not just to health, but around migration issues as well. The second new super users, British Red Cross. British Red Cross are part of a wider movement of Red Cross and Red Crescent societies around the world who help people prepare for, respond, and recover from extreme weather. So that talking about extremes just then in the questions is really topical issue for a lot of users because we see these big impacts from extreme weather onto our lives. So things like droughts, heat waves, wildfires, flooding are key issues for organisations like British Red Cross. And so the focus on extremes in aspects will be really important. So in the past, Red Cross societies have typically been using weather and maybe seasonal climate information in their short-term decision making. But British Red Cross are really looking at how to use insight on longer term timescales, looking at climate timescales, the next 5 to 10 years or longer, so that they can adapt as an organisation in their decision making and making preparations so they will be able to cope with the changes that they will see to their responding over the coming years as we may have more increased frequency of extreme events. So this is a an organization being proactive in how they are trying to change. And so we're very excited to work with them to help them improve their capacity to respond and adapt to climate change. And we are, of course, going to try and engage beyond the Red Cross and use the partnership that they have with the International Federation of Red Cross and Red Crescent Societies across Europe. In particular, there is a specific technical reference group for climate action in Europe, which is currently being chaired by the Spanish Red Cross and co-chaired by the British Red Cross. So this engagement will help support input from all the European Red Cross and Red Crescent societies into the development of the aspect study. And British Red Cross themselves will also be able to use the evidence and insights that they've gained in this case study with us to advocate for broader changes to policy and practice and share the learning as well. So again, you can see how these two new organisations have extended our diagram around case studies for seamless decision making.
Thank you, Freya. We are delighted, in fact, for having you in this project. And I would like also to thank you, Freya and Bina, again for providing all this information on how Aspect engages with our super users and what opportunities provides to other end users. At this point, we can also move forward.
Super. Thanks very much, Panos. Yeah, I'll get on with it because I'm aware that there isn't a huge amount of time. So yeah, good afternoon, everyone. So in this really brief talk, I'm really excited to share with you some initial insights from a quantitative survey that was conducted by myself and colleagues at the University of Leeds and partners within the Aspect project. So conducted at the end of last year, this survey explores how different sectors and organizations across Europe are using climate information to respond to weather and climate risk. I should say, however, before I begin, that we are still analyzing the findings, so I'm only able to give you a general, what we call a descriptive overview of some of the headline results. So let's start by looking at the composition of our survey sample and the criteria we used for screening out respondents. Firstly, our screening questions. To ensure we collected relevant data, we focused on individuals whose organizations are sensitive or impacted in some way by weather or climate. We also sought respondents who had at least 1 year of experience in their respective sectors to ensure that they had enough of an understanding of their organization's activities. This left us with a total of 1,773 respondents. Moving on to the characteristic of our sample. Working with the sample recruitment company, we aimed for and achieved a broad representation of countries from across Europe, with a particularly strong presence from countries with larger populations and economies, such as Germany, the UK, France, Italy, and Spain. Interestingly, 9% of responses were from Danish organizations, which may indicate higher awareness of climate sensitivities, or perhaps our sample recruitment company just found it easier to recruit Danish companies, organizations. It's really difficult to say. I just thought I'd make that point. In terms of roles and positions within these organizations, our respondents varied widely. Around 20% were owners, 40% held senior or managerial positions, and about 30% were technicians or planners. This distribution gave us a broad perspective of how climate and weather information is being used at different levels within an organization. Regarding their experience, 63% of our respondents had between 1 to 10 years experience in their field, with 36 falling in the 6 to 10 year range. This experience mix provided us with insights from both relatively new and experienced staff. Most of our respondents, around 63%, came from large private companies operating at national or international levels. We also had participation from smaller companies representing approximately 15% of our sample, and public sector organizations, international organizations making up approximately 18%. So bearing in mind respondents could select multiple sectors, when asked how they would classify their organization, the most frequently reported sectors were manufacturing, construction, transportation and storage, and information and communication, which together represented over half of our sample. An interesting aspect we explored was the planning horizon of these organizations for significant decisions, such as choosing locations or making major investments. Most respondents reported planning horizons between 1 month and 10 years, with the most common range reported by 20% being between 2 and 5 years. This potentially highlights that organizations are adopting a range of strategic approaches in the face of climate risks. So as you can see, it's a pretty diverse sample. Now let's sort of dig into the findings a bit more, shall we? Firstly, how organizations are impacted by weather and climate. We asked respondents which weather events or long-term climate trends out of 35 different options has most significantly impacted their organizations in recent years. Extreme heat emerged as the most impactful, affecting 15% of organizations surveyed. This was followed by heavy rainfall at 8% and a warmer overall climate at 6%. The fact that almost every option was selected by at least 10 respondents highlights the wide range of climate sensitivities present across European organizations. We also asked respondents how their organizations were affected by climate. Bearing in mind that respondents could select multiple options, the most significant effects were seen on people, so their workforce or their customers, at 43%. Then it was their premises, so maintaining their buildings at 34%, and then processes also at 34%. So this was things like production and service delivery. These findings highlight the diversity of impacts on organizations. We also asked respondents about these same specific events or trends relevant to the information they used. Consistent with earlier findings, the focus was again on extreme heat, heavy rainfall, and warmer climates. Interestingly, there was also a noticeable demand for information on cold snaps and fog forecasts, suggesting some niche climate information needs among the respondents. So now I'll go into a bit more detail on information use. So firstly, we asked respondents whether they use weather and/or climate information. 77% of respondents confirmed that they are actively using weather and/or climate information in their roles. Among those not using, over half believe they might require it in the future. In total, then, nearly 90% of all respondents either already use or recognize the potential value of using weather and/or climate information. We then asked respondents not interested in using weather and/or climate information for reasons for non-usage. While it's worth noting that respondents could select multiple reasons, 54% indicated that such information was not required in their role. Expense and doubts around its usefulness were also identified as prohibitive factors by around 50% of those asked the question. Among the respondents using information, 61% reported are using weather information, so just mainly weather information. The next most frequently used types were observations, subseasonal forecasts, and seasonal forecasts. Reanalysis, interannual and decadal predictions, and climate projection information are currently less commonly utilized. And also, I just wanted to point out, you can see there on the left, there are 70% of the respondents only use weather forecast information. So I just wanted to sort of clarify that. That's quite an interesting point. So we inquired, about where they get weather and climate information from. So national Met services scored very highly on this question, especially for weather forecasts. For subseasonal and interannual predictions, however, private companies were more frequently reported. So this aligns with our separate finding that nearly 3/4 of information users pay for such information. Some respondents indicated they received seasonal and interannual predictions from the Intergovernmental Panel on Climate Change, the IPCC, although the IPCC doesn't actually provide this information. So this is kind of a strange finding. It could be something to do with maybe the familiarity of the IPCC and people not really knowing where they're getting their information from. It's hard to say, obviously, without talking to them and exploring it a bit more on an individual basis. But yeah, that's some sort of, speculation there. Respondents were asked how frequently they use different types of weather and climate information. So we found that over half of the weather forecast users utilize these forecasts on a daily basis. In terms of the other types of information, the predominant usage patterns were weekly, monthly, or every 6 months, with monthly usage being the most common across most other types of climate information. We asked people what they used weather and climate information for. And it turns out that informing long-term strategic planning is the top reason, particularly among those who use seasonal forecast information. And for weather forecast, the primary purpose identified was informing risk management. So that's pretty much as we would expect and sort of in line with previous assessments. Respondents were prompted to select from a list of 12 areas where they felt improvements in weather and climate information or services were needed. While there was a wide range of options selected, 1/3 of respondents emphasized the need for easier to understand information. This points to a significant demand for better communication and presentation of climate information. Other crucial areas for improvement identified were the reliability and accuracy of forecasts, along with their timeliness and accessibility. Again, this is in line with climate services literature around sort of, improvements in climate services going forward. And then finally, we asked respondents about their confidence in using the best available information with a rating scale from 1 to 4. Interestingly, about 72% indicated they are confident or very confident in the relative quality of the information they utilize. So, to sum up, European organizations are significantly impacted by a wide range of weather and climate conditions. These organizations extensively utilize climate information primarily for strategic planning with a horizon of up to 10 years, and weather forecasts are also used widely for risk management. The main sources of this information are national Met services and private companies. And there is, however, a clear need for improvements in the understandability, reliability, accessibility, and timeliness of this information. Okay, so to finish off, we haven't got a huge amount of time here. We'd really like to hear your thoughts, and given these time constraints, we can't delve into discussion right now really about it. It would be great if you could scan this QR code and leave your comments. I'm sure some of you participated perhaps in this survey, so it'd be really interested to know how these insights align with your experiences. Thank you. I'll just leave that on the screen there for people to scan. Thanks, Panos.
Thank you to you, Sam. Thank you very much for this insightful contribution.